So I'm going to start you all off with a problem that is guaranteed to be on the Tavernetti practice or actual exam. So you all should definitely practice this right now and probably a couple more times if you're not comfortable with it before the test. But I want you all to do this right now. Find the derivative of tangent of 9x. Doing it the long way, meaning writing tangent in terms of sine and cosine. So find the derivative of tangent of 9x the long way. So I'll even help you out. I'll give you one step here, although you're going to have to do the step on your own. It's the derivative of sine of 9x divided by cosine of 9x. Now go ahead and use the quotient rule and do the rest. I'll give you 2 minutes. You will have to use a trig identity. Get things a little bit more situated here. Pencils down. You get 10 more seconds. All right. So again, I'll stress for those of you in Tavernetti's class, you should practice each of these so that you can do it like that, because it's going to be probably the first question on your next test tomorrow. So quotient rule, bottom, derivative of the top, make sure we take the derivative of sine of 9x. You also have to use the chain rule, the derivative of sine of some stuff, cosine of the stuff times the derivative of the stuff. Minus, then we flip it, top, derivative of the bottom, the derivative of cosine of some stuff is negative sine of that stuff times the derivative of that stuff, all divided by cosine squared of 9x. Now, here's where you could probably get away with being a little bit slick. You could say, you know what the answer is going to be here. You know this is going to end up being not 9 secant squared of 9x. But I would probably, if I was pressed for time, I would probably just say, okay, yeah, that's going to equal 9 times secant squared of 9x. But I would imagine he'd probably like to see one more step here. Factor out the 9. And then you've got a cosine squared of 9x. Minus times a minus is plus sine squared of 9x. All divided by cosine squared of 9x. And then I probably would just say, oh yeah, that's 1. So this is equal to 9 over cosine squared of 9x, which is equal to 9 secant squared of 9x. So you could probably get away with showing 1 or 2 less steps here, but you definitely need to have this step and then this last answer because it's supposed to equal to that. Let's do one more. Let's do one of the other varieties, which is not tangent or cotangent, where you have, so for tangent or cotangent, you're going to have this identity show up. Cosine squared x plus sine squared, cosine squared of whatever plus sine squared of whatever equal to 1. And for the cotangent one, it'll be negative cosine squared minus sine squared, you'll have to factor out a negative whatever, like a -9 or a negative whatever your value is. Let's do the other one. In fact, I want you all to do this one as well. So in the same sort of way, I want you all to find the derivative of cosecant of 2x. And you're first going to have to write it as not just 1 over, but the derivative of 1 over sine or cosine. Nikki, I'm asking you because you're the person in class. It's sine. So everybody, I'll give you 2 minutes again. Find the derivative of 1 over sine of 2x. And you should be doing this at home. If you're not in Tav's class, it's still good practice. Welcome, welcome. We are currently finding the derivative of cosecant of 2x the long way, which will definitely be on Tavernetti's exam tomorrow. Come on in. Come on in. Give it another 30 seconds. Oh, I see Peyton and Erica. There are lots of folks on Zoom, which is great. Hey, everybody on Zoom. Hey, everybody in class. All right. So again, I'll wait till they get here soon. So we're just talking about finding the derivative of cosecant using the quotient rule, the way you're going to have to do it on your test tomorrow in Tav's class. So for cosecant and secant, so I will say tangent and cotangent kind of follow the same pattern. Secant and cosecant kind of follow the same pattern. It'll probably be, you might have one of each, you might have just one of all four. So for this one, you have to write it as a quotient, 1 over sine. I will point out, you could write it as sine of 2x to the -1 power and use the chain rule, but I would recommend doing them all using the quotient rule. It's just easier because the quotient rule will work for any of them. Whereas like for tangent and cotangent, you could do it a different way, but you have to use the quotient rule for tangent and cotangent. For secant and cosecant, you could get away without using the quotient rule. I still think you should. I think it's going to be easier just to remember doing them all using the quotient rule. So using the quotient rule, it's going to be the bottom times the derivative of the top. And I do recommend writing out the bottom times 0 minus the top times the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff, all divided by the bottom squared. And I will say, I feel like simplifying this one is actually the harder one to do. So what you could do here, I think, is jump to what you know the answer is. I think you'd be like, oh yeah, this is definitely going to simplify as exactly -2 times, what's the derivative of cosecant? Cosecant cotangent. -2 cosecant of 2x plus u cotangent of 2x. I think you could go from there to there and you probably would be just fine. Unless he says that's not okay. If you want to show 1 or 2 more steps, here are the steps you could show. I would write this as -2 times cosine of 2x over sine squared of 2x. And then here's what you should be thinking. I know I want the answer to look like that. I know I need a -2 and a cosecant and a cotangent. So great, I'm going to make it happen. I'm just going to be like, well, it's going to be -2. Cosecant is 1 over sine, so I need a 1 over sine. And cotangent is cosine over sine, so I need a cosine over sine. And because I know I'm supposed to get the answer, I'm sure that this is the right way of breaking it down. And it is. If you multiply out the top, you get -2 times 1 times cosine, which is what we have on top. Multiply at the bottom, you get sine times sine, which is sine squared. But you don't have to think about how this actually breaks down. You just have to think about what you need the answer to look like. So I would highly recommend for all of you in Tav's class, sometime before tomorrow, you should do the following on your own. The derivative of cotangent of 6x, the derivative of tangent of 4x, the derivative of secant of 3x. We'll make this also one spicy here. The derivative of cosecant of -4x. Ooh. You should practice all of those. You know what the answers are supposed to be, but you should do it the long way so that you can do that first problem that's going to be on your exam like that. Because he wrote it in the practice. One of those 4 is going to be on your test. I mean, you know something's going to be on your test. Spend enough time practicing so you'd be like, oh yeah, I'm done. We're in the books. Any questions about this before we move on to other stuff? All right, so I'm happy to take requests from any of the practice exams or just start going through them. And that includes the ones for Tamara Galiava's class as well, right? If you're in her class and you have questions you want me to address, yep, I'm happy to. So if you have questions and you want to get, like, you should start writing them in the chat. I have all the exams with me if you have a specific exam you want to refer to, Michaela, or you can type it out. That's also fine. Yeah, Nikki. Yeah, totally. And I will post solutions to the ones I posted. I just haven't written them yet, so I can't put them just yet. But yes, did you have a specific one in mind? Okay. Also, I do have copies of the exam that you're all welcome to take with you when you leave. Then you can look at it. Sorry, let me grab it. Yes, go ahead, Nikki.
It's problem 3.
Yeah, we'll get that, Michaela. Problem 3. Sure. And so obviously I tried to write this one very much like his exam. Oh yeah, problem 3 is a long one. So we'll do problem 3 here and then I'll come back to your question, Michaela. So problem 3 for the, oh yeah, and this one I wrote a little bit differently than his because I thought I wanted to change up a little bit. So for the following problems, we have that this is 3 from my exam. I will admit I wrote this kind of fast, so it's possible I wrote something that wasn't excellent. So we will address that if it's an issue. So f of x is x squared over x minus 1, and g of x is the square root of x minus 1. And actually, I think, let me address Michaela's question because it does relate to what we just did. So we'll get to this in just a second. So just to address your question, Michaela, you asked, are we able to take the derivative from cosecant of 2x right away, or should we always simplify beforehand? Well, so here's what I would say. For Tavernetti's exam, he's specifically going to ask you to take one of these derivatives by writing it in terms of sine and cosine. So normally, like for a product rule or quotient rule or some other thing, right? Like if it was just taking the derivative of cosecant for other reasons, like trying to find its maxima or minima, you would just take the derivative of cosecant of 2x as what we've memorized, which is -2 times cosecant of 2x times cotangent of 2x. But for this specific question, he is asking you to write it in terms of sine and cosine. So we first have to rewrite cosecant, not take its derivative, just rewrite cosecant of whatever as 1 over sine of whatever. And then take the derivative using the quotient rule. So bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. And then after that, we then have to simplify it so that we get the answer we know we're looking for, which I think you kind of just jump to, but you might want to show a step or two along the way. And then there was another question there. Do I have any tips to figure out if a side is positive or negative in the sign chart? Yes, and we'll get to that in a minute. I do have some tips. Okay, I'm gonna minimize this. Let's go ahead and look at question 3 here. No, so I will tell you, so there's definitely something you're expected to know, but I will tell you, right, the derivative cotangent of 6x is going to be negative cosecant squared of 6x times 6. You can write the 6 in the front, but I like to write it at the end. Derivative tangent of 4x is going to be secant squared of 4x times 4. The derivative of secant of 3x is going to be secant of 3x times tangent of 3x times 3. And the derivative of cosecant of negative 4x is going to be, this is where this one's a little bit spicy, because it's going to be negative cosecant of negative 4x times cotangent of negative 4x times negative 4. So the final answer is going to be positive 4 times cosecant of negative 4x times cotangent of negative 4x. So definitely practice each of these. Start with that. Write it as cosine over sine. Write that one as sine over cosine. Write that one as 1 over cosine. Write that one as 1 over sine of whatever the argument is, and then take the derivative using the quotient rule. Okay. All right, let's look at this question I wrote here, which there we go. Sorry. Yes. So what is the domain of f and g? Cool. So the domain of f. So for the domain of f, well, we just have to look at where the denominator is 0. So we know that x minus 1 can't equal 0, or in other words, x can't equal 1. On a number line, that means we get everything except for 1. So we want all of this, we want all of this. You don't have to draw this, but it helps me see that, oh, I want everything from negative infinity to 1 exclusive, union 1 to infinity. You definitely are expected to write your domains in the interval notation. So if you just write x not equal to 1, you'll probably get some partial credit, but the expectation is you write the domain like this. And the domain of g. So for g of x, we know that the inside stuff has to be greater than or equal to 0, because we need to take the square root of non-negative numbers. So here we need x to be greater than or equal to 1. So if we wanted to draw a number line again, there's 1, but now we're including 1. We want everything that is bigger than or equal to 1. So our domain here is 1 with a bracket, comma, infinity. Infinity always with the parentheses, because it's not a real number, so we can't actually include it. Okay, what's the next part of this question? Ooh, yeah, I asked some good questions here. Is x equal to 2 a critical point of either of these functions? So the question here is, 1, is x equals 2 in the domain? It certainly is for both of these functions. But 2, if you take the derivative and plug it in, is it going to equal 0 or undefined? Let's check it out. So what this is really asking us to do is to take these derivatives here, and I probably need a little bit more room. So let's get ourselves another piece of paper here. So let's look at f prime. Quotient rule again. So bottom, derivative of the top, minus the top, times the derivative of the bottom, all divided by the denominator squared. I might do a little bit of simplifying here, just to make it a little bit easier to plug in. So f prime of x is equal to 2x times x is 2x squared. 2x times negative 1 is minus 2x, minus x squared, all divided by x minus 1 squared. And doing one more simplification, f prime of x, 2x squared minus x squared is just x squared minus 2x, all over x minus 1 squared. So now, if x equals 2 is a critical point, what should happen when I plug it in to the derivative? I should either get, or maybe undefined, right? Because you can have a critical point where the derivative is undefined. So f prime of 2 is equal to 2 squared minus 2 times 2 over 2 minus 1 squared. Oh yeah, that is equal to 0. 4 minus 4 is 0 over 1, which is 0. So yes, x equals 2 is a critical point for f of x. You can't see what I'm writing. What about for g of x? Well, g of x was equal to the square root of x minus 1, which I would rewrite as x minus 1 to the 1/2. So then g prime is going to be 1/2 times x minus 1 to the negative 1/2. And if you prefer, You could rewrite this as 1 over 2 times the square root of x minus 1. Or 1 over 2 times x minus 1 to the 1/2. Which you might have to do if he asks you to write your derivative so you don't have any negative exponents. All right, if I plug in 2 here, g prime of 2 is going to be 1 over 2 times the square root of 2 minus 1, which is definitely 1/2, which is not 0 and not undefined. So x equals 2 is not a critical point for g of x. Yeah, Nikki, what's up? Okay.
Oh, yeah, how come you didn't take the chain rule inside of that?
I did, but I didn't say anything about it because when I multiply with the derivative of the inside, what is the derivative of the inside? What is it? Right, it's 1. But yeah, you're right. We should be thinking about the chain rule all the time here. So it's just sometimes the inside has a derivative that is 1. So we kind of just don't say anything. Okay, same question for x equal to 1. So the nice thing about this next one is we don't have to do the same work again. So let me ask everybody. Thumbs up for yes, thumbs down for no. Is x equal to 1 a critical point for f of x? Thumbs up for yes, thumbs down for no. Well, I tricked you all. It is not a critical point. And here's why. But it's good to know. It's not in the domain, right? The original function, x equal to 1, is not in the domain of the function. And that is the first thing that has to be true to be able to be a critical point, is that it has to be in the domain of the original function. So x equal to 1, no. F of 1 is undefined. Not f prime, although f prime of 1 is also undefined, but since f of 1 doesn't exist, can't be a critical point. Okay, now here is the same question for g of x. Is x equal to 1 a critical point for g of x? Thumbs up for yes, thumbs down for no. Yes, it is this time because 1, g of 1 does exist. G of 1 is equal to the square root of 1 minus 1, which is 0. I don't care that it's 0 or 5. I just care that it exists. 1 is in the domain of g of x. And more importantly, g prime of 1 is undefined. Well, that exactly qualifies. If the function is defined somewhere and the derivative is either equal to 0 or is, then we have a critical point. And we're definitely meeting that qualification here. G prime of 1 is undefined and 1 is in the domain. So we're good. All right, let's look at the last one. I think the last one was x equal to 0. And I think we can squeeze it in here. So how about x equal to 0? Well, again, if I plug in 0, well, first of all, 0 is in the domain, right? 1 was the only thing that was questionable. F prime of 0 is equal to, let's see, 0 minus 0 over 1, which is definitely 0. So yes, x equal to 0 is a critical point for f of x. What about for g of x? I don't love, yeah. So here's kind of a weird thing to say. If I plug in 0 for g prime, it is undefined, but not in the right kind of way. When you're taking a square root of a negative, that means things are dicey. Really, we should go back and look at the original function. Oh, 0 is not in the domain of the original function. So definitely not. 0 is not in the domain of g of x. Yeah.
How is x of z equals 0 in the domain for f of x?
Well, look at the original function. If you look at the original function, the only thing that's out of bounds is x equal to what? Right. 0 is totally fine. If you plug in 0, you get 0 over -1, which is 0.
Oh, oh.
Good? Cool. All right. And then there was a question from, so that's question 3, right? Yeah, that's question 3. There was a question from Anthony. Let me remind myself what it was. Tips to figure out the side. Yeah, okay. So let's look at, do I have a good example for that? Let me think for a second here. I think I do. Let me, yeah. Oh, yeah. Okay, sure. I think this question is, yeah. Let's look at this other function I've got here. So I'm gonna look at question 4 from the practice exam I wrote. I think it does a decent job of asking and answering the question you've asked, Anthony. So let's look at, yeah, is it? Sure. Let's look at f of x equal to x squared minus 9 to the 1/3 power. And we want to find all the sign charts really. So I will point out, when you have an odd root, you don't have to worry about things being positive or negative, right? The insides can be negative, the insides can be positive, and you can always take the cube root of any real number, a 1/5 root of any real number, as long as it's real. So if I want to make a sign chart for this, for f of x, because it's not terrible to make a sign chart for f of x, I kind of want to factor this as much as possible. So I can factor the insides as x minus 3 times x plus 3, all to the 1/3 power. Roots get a little bit weird, but the thing I was going to say is that we know that the sign changes when you go from one side of a root to the other side of a root if the factor it came from has an odd power. And it doesn't change if the factor it came from has an even power, or I should say it stays the same if the factor had an even power. So if I start making a sign chart just for f, my critical points, or my zeros, I should say, because they're not really critical points, they're just where the function's equal to 0. My x-intercepts are going to be 3 and -3. And then I do usually have to pick one point. So if I pick a point larger than 3, because I like to start as far right as possible, I find that to be the easiest. You don't have to make that choice. If I pick a number larger than 3, like 4 minus 3 is positive, 4 plus 3 is positive, multiply them together is still positive, and a positive number to the 1/3 power is still positive. Like 8 to the 1/3 is 2. A negative number to the 1/3 power is still negative. Odd roots preserve signs. Even roots, you don't get to take the square root of a negative number. Okay, so we know it's going to be positive over here. And then instead of repeating that process by picking like 0 and -5, we're instead going to say 3 came from that factor. That factor has an odd power, which means the sign is going to change. -3 came from that factor. That factor also has an odd power, so the sign is going to change yet again. So currently we know that our function is above the x-axis, left of -3, below the x-axis between -3 and 3, and above the x-axis to the right of 3. Right? This is just the sign chart for f, not for f prime. We're not talking about increasing or decreasing yet. Well, let's go ahead and talk about increasing or decreasing. So let's go ahead and find the derivative. Now, usually it's nice to factor things so that we can see what's happening, but it's usually nicer to take the derivative of the unfactored form because I don't want to use the product rule unnecessarily. So for our first derivative here, it's going to be 1/3 times our stuff to the -2/3 power times the derivative of our stuff. And I believe I did say, no, I guess I didn't say, but I wouldn't be surprised if he wanted you to write this with positive powers. So writing this so everything has positive powers, we're going to rewrite this as 2x on top, and on the bottom we're going to have that 3, and then we're going to have x squared minus 9 to the 2/3 power. And then I do think it is worth your while to factor this. So here's where the factoring gets kind of funky. And maybe this problem, I don't know, this problem I don't think is great, but it is fairly similar to one he put on his practice exam. So it's maybe not the best, but it's not terrible. So if we factor the bottom, you guys should watch this for a second. So inside that 2/3 power, x squared minus 9 is going to factor the same as it did before. X plus 3 times x minus 3. but then each of those things is raised to the 2/3 power. So I would actually write this as 2x over 3 times x plus 3 to the 2/3 times x minus 3 to the 2/3. Okay, show me on your fingers, how many critical points do I have? Yeah, I think that looks good. We definitely have 3. -3 is still a critical point, +3 is a critical point, and 0 is also going to be a critical point. So my critical points or critical values are x equal to 0, 3, and -3. And I want to point out 3 and -3 are real critical points. They're in the domain of the original function, and they make the derivative equal to undefined. I shouldn't say equal to, they make the derivative undefined. Saying equal to undefined is terrible. That's just my own personal pet peeve, though. So, sign chart for f prime. Now, here's where the thing I was saying before is going to be a little bit harder to maybe digest, but not that hard. Again, pick a number larger than 3. I'm going to pick 4. Plug it in to the fully factored form, but you're not really actually plugging it in. You shouldn't write down anything when you plug it in. What you should do is be like, okay, I'm picking 4. I'm plugging it in. I can see that the top is positive. I can see that the bottom is 7 to any power is going to be positive, and 1 to any power is going to be positive. Positive numbers to any power are still positive. Let me say that again. Positive numbers to any power are still positive. So that means it's positive over here. Great. Now, here's where the thing I said before is a little bit harder to see. 3 came from that factor. That factor, yes, it has a fractional power. But if you look at the numerator part of it, is the numerator part even or odd? Even. Oh, okay, so you're squaring it, which makes it positive, and then you're taking a cube root, and a cube root of a positive thing is still positive. So the fact that you're squaring it first or second means it's going to have to end up being positive there. So essentially, we're going to stay the same because this thing here is raised to essentially an even power. If you don't like that, you can plug in a number. Plug in 1. Positive, positive, positive. 1 minus 3 is negative, but a negative number squared becomes positive, and the cube root of a positive is still positive. Or, if you like, a negative number cube root is still negative, but then you square it and becomes positive. So all positive. All right, other side of 0. 0 came from this factor, which is raised to an odd power, so the sign's going to change. Also, another way you could look at this without doing quite as much work is notice that the denominator is always going to be positive. You have some stuff raised to the 2/3 power, always positive, no matter what you plug in for x. So really, it just depends on the numerator. And the numerator is positive when x is positive and negative when x is negative. So our function is decreasing, decreasing, increasing, increasing. Which means if we're talking about classifying critical values, we have a relative what at 0? A maxima or a minima? A relative minimum at x equal to 0. And at the other 2 critical points, we have neither max, and I do think he wants you to probably write this, neither a max nor a min at x equal to plus or minus 3. And I probably made this one more challenging than I needed to. But let's go ahead and look at, the second derivative is going to be gross. We might have to abandon. No, we'll do it. It's not too bad. So let's do the second derivative and talk about concavity. So, yeah. So again, if I'm finding the second derivative, I'm going to use the nicest looking one I can think of. That to me looks like the nicest piece. I would rather not deal with the bottom being factored. I will make one other small adjustment. I'm going to rewrite f prime, and I'm going to factor out the 2/3 in front. Because if you have a constant multiples just get to hang out. So let's write f prime as 2/3 times x over x squared minus 9 to the 2/3 power. I think that's going to be a little bit nicer to deal with. And you're welcome to do this if you have a constant multiple on top or on the bottom. You can just pull it out. Still has to stay there, right? It doesn't go away. But when we take the derivative, that 2/3 just gets to hang out in front. Okay. Quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom is going to be 2/3 times x squared minus 9 to the negative 1/3 times the derivative of the inside stuff, which is 2x, all divided by x squared minus 9 to the 2/3 squared. And if you have something raised to the 2/3 and you square it, what's the new power going to be? 2 times 2/3, which is 4/3. Right? When you have a power to a power, we multiply the powers. Okay, this one is definitely, I mean, the derivative wasn't great, but the real challenging part of this problem is the simplifying. To be able to find the critical values, you have to actually simplify this, which is not an easy task, but let's do it. Also, to be able to make the sign chart correctly, we have to simplify this to make it even plausible. So looking at the numerator here, I see I can factor out x squared minus 9 to some power. What power can I pull out? Should I pull out the biggest power or the smallest power? You're right, Peyton. Say it louder. The smallest power, always the smallest power. So I'm going to pull out an x squared minus 9 to the negative whatever, because a negative number is always smaller than a positive number. So we're going to factor out. So we've got a 2/3 out in front. And then in the numerator, I'm going to factor out an x squared minus 9 to the negative 1/3. Okay, so what am I left with here? Well, here I'm left with an x squared minus 9 to the 2/3 minus negative 1/3 is 2/3 plus 1/3, which is 3/3, which is 1. Which again, if you multiply those back together, you would add those powers and get 2/3 as your power. It's a good mental check to do that. And then over here, this completely factors out. So I'm left with an x times a 2/3 times a 2x, which is kind of gross. So x squared times 2/3 times 2 is x squared times 4/3. So 4/3 times x squared. Ugh. All divided by x squared minus 9 to the 4/3 power. And then we're going to bring that down to the bottom to get x squared minus 9 to the 5/3 power. Because we're going to add the 4/3 and the 1/3, right? Because that becomes positive when you bring it down. So simplifying this, I'm going to show you a way to make this not quite as gross as I have made it here. I'm going to have the denominator is going to be x squared minus 9 to the 5/3 power. And then on top here, x squared plus 4/3 x squared. Here's what I would do. I would multiply the top and bottom by 3. Totally allowed. If I multiply the top by 3, I'm not even going to simplify it. I'm just going to write it as x squared minus 9 plus 4/3 x squared. Because of that 3 right there, right? That's why I'm doing this, to get rid of that 3, because I really, really don't love it. And then multiply by 3 on the bottom. Okay, so now making this a little bit less gross. Distributing the 3, I've got 3x squared minus 27 plus 4x squared. All over the same denominator I had before. Sorry, this problem's a little bit gnarly. And then finally, bringing out this 3, I've got a 2/9 times 3 plus 4 is 7x squared minus 27 all over x squared minus 9 to the 5/3 power. You can probably skip this one on the practice exam if you try it later. It's at least this part of it's a bit much. Okay, but finishing it off, if I want to find the critical values for the second derivative, I'm still going to get 3 and negative 3. I'm also going to get where the numerator is equal to 0, which unfortunately does have solutions. They are gross though. If we set 7x squared minus 27 equal to 0, we get 7x squared equal to 27. x squared is 27 divided by 7, which is almost 4. I wish it was 4. It's not 4. Oh well. And then x is plus or minus the square root of 27/7. How terrible. And then you can make your sign chart for your second derivative. Now here's the good news. Is it good news? Sure, it's good news. The good news is the sign chart for the second derivative is not that hard to figure out what's going on here. So we've got our 4 critical values. Is 0 a critical value for the second derivative? I mean, did I list it? Yes or no? No. So don't put 0 on your sign chart. That's what I'm trying to find here. If 0 is not a critical value, you don't want to put it on there. It's just going to get in the way of everything else. So we've got 3 and -3, and ooh, yeah. Those should be the bigger ones, James. How do I know they're bigger? Well, I said this was almost 4, and the square root of almost 4 is almost 2. So those should be the negative square root of grossness, the positive square root of grossness, and then the 3 and the -3. Okay. So looking back at our second derivative here, which is 2/9 times 7x squared minus 27 over x squared minus 9 to the 5/3 power. Pick something bigger than 3. Pick something gigantic. Pick 1,000. 7 times 1,000 squared is 7 million. Okay, at the top is positive. 1,000 squared minus 9 is definitely positive. To any power is still positive. All right, are we going to change or are we going to stay the same? Eesh. Well, if we do a little bit of factoring, the bottom factors is x minus 3 times x plus 3, and they're each raised to the 5/3. Well, now the 3 came from there. It's raised to an odd power and has an odd root, means the sign is going to change. And then the sign is going to change again when we cross this, because you could factor this, although I don't really want to, as x minus the square root of 27/7 and x plus the square root of 27/7, but they're both raised to the first power. And so we're going to change again, we're going to change again, we're going to change again. So it's concave up, concave down, concave up, concave down, concave up. How many inflection points do we have? You do have enough fingers to show me. Yep, that many. Yep, that many. There are 4 inflection points. Let's not list them all. There they are. All 4 of those critical points. Okay. The question does ask, where is f increasing? So back to the first derivative for a second. And we'll come back to this, don't worry. Don't worry, we're not done yet. The function is increasing. Ooh, good question. So let's answer this over here. Sorry, no, terrible anyway. So f is increasing. All right, here's your choice. Is it increasing from 0 to 3 union 3 to infinity, or is it increasing from 0 to infinity? One of those is right. One of those is not. Here's what the answer is. The answer is this one. Why is it this one? Well, because it's increasing, and the function is defined at 3. If you graph this thing, it looks kind of funky, but it's definitely right. If you plug in 3, you get 0. So since it's increasing, and the function is defined at the point in between those 2 intervals, we include it in the interval of increases. Whereas, just as a counterpoint, if your function looked something like this, where you had like say a vertical asymptote at 3, and it was increasing, then you couldn't include the 3, and you'd have to say it was from 0 to 3 and then 3 to infinity. All right, so that's where it's increasing from 0 to infinity. As far as we're concerned, whenever you're talking about increasing or decreasing, it should always be an open interval. You're never including the endpoint. unless your teacher has said something different, but I don't think he has. I'm pretty sure he's on the same page as far as that goes. Some people say weird things about endpoints sometimes. And then similarly, concave up is what I asked. Yeah. Okay, concave up is going to be annoying to write, but it's concave up from negative infinity to -3 union negative square root of 27 over 7, comma square root of 27 over 7 union 3 comma infinity. Apologies for the terrible numbers. I will admit this was the last question I wrote as I was trying to get out of the office yesterday to get somewhere. So wasn't the graph looked nice, but the numbers apparently are not as beautiful as I hoped they were. All right, and then finally, the question is, on which intervals is f of x concave up and decreasing? Okay, well, looking back at our work, actually, let's just draw it over here. We know that f prime looked like this. And it was negative, negative, positive, positive. So decreasing, decreasing, increasing, increasing. So it's decreasing over here on the left of 0. And then here, I want it to be decreasing and concave up. So I'm looking at this and half of this, right? Because it's decreasing definitely here from negative infinity to -3, and definitely here from negative whatever to 0. So the answer to the question where it's decreasing and concave up is going to be from negative infinity to -3 union negative terrible number to 0. Which I feel like is kind of a tricky question, but he definitely does ask one like that in his practice exam. So it seemed worth looking at. And I didn't actually look at the solution to his practice exam, but I imagine it would be the same sort of thing where there's going to be some overlap, but it's not going to be perfectly overlapping. So you have to kind of actually break up one of them into like less than it would be the whole interval. So hopefully, Anthony, I know that was a very long answer to your question about intervals, but as far as like determining whether things are positive or negative, I really like to look at the factor that the 0 came from or the critical value came from. And then by looking at the power of that factor, if it's an even power, the sign is going to stay the same. If it's an odd power, the sign is going to change. Just as a kind of more general statement, someone had asked me in the reflections to talk about kind of test taking strategies. So just a couple things that I want to remind you about. If you get stuck, move on to the next thing. Come back later. I wouldn't spend tons of time simplifying stuff. If you feel like you've gotten to a place where an answer is good, move on, come back later. But really, the advice of not getting stuck is probably the most important thing I can say. Don't let yourself get stuck. If you find yourself getting stuck on a problem, move on to something else. Working on other stuff will bring out the knowledge that you have about the other things. So keep working. Don't let yourself get stuck. I feel like there was one other thing I really wanted to say too, but it's escaping me at the moment. Get a good night's sleep if you can. Try to eat some breakfast. What time is your test at? 3:10. Okay, so try to eat some lunch. For those of you, I don't remember what time the other class has their test at, but definitely do the normal things to prepare yourself for your exam. Good. Glad, Anthony. All right. Yes.
Do you have topics?
I do. Yeah, let me just make sure. So I've got stuff all over the place here. Cool, that's mine. Problem 2. Where'd you go? I had it. You think I know I have it. One moment. There, not there, not there. Right there. Right in front of my eyes. Literally with the word tabernacle. Let's look at number 2. Oh yeah, I think it was some related rate stuff. Yeah, cool. That's what it looks like. Okay, number 2. I will point out these related rates problems to me look, I don't want to say easy, but easy in that you're not being asked to set up anything geometric here, right? You don't have like a dude walking away from a light post or a cone being filled with water or whatever. He's tried, and I mean, I can't imagine he's going to go from this to something that is harder, like where you would have to set it up. So hopefully that's an indication that you shouldn't have to worry too much about the setting up part of a related race problem, but the execution. So the point is moving along the graph of y equals 1 over 1 plus x squared. We're given that dx dt is 2 inches per second, which I'm going to write down again. And we're asked to find dy dt. I always think it's a good idea to write down the d what's, the things you know, the thing you know is changing, and the thing you want to know. And then we're given that y equals, I might rewrite it as 1 plus x squared to the negative 1, personally. But we can do it the other way as well. Should I plug in x equals 3 right now? No, I need to take the derivative before I plug anything in. Okay, we're going to differentiate both sides. What's the derivative of y? I'll remind you, we need both of these things to show up in our next step. So what's the derivative of y? It's the derivative of y. What's the derivative of some stuff to the negative first power? It's negative 1 times our stuff to the negative second power times the derivative of the stuff. What's the derivative of 1? What's the derivative of x squared? Well, let me say, what's the derivative of some stuff squared? 2 times your stuff to the first times the derivative of your stuff. If you get to this step and you don't have both of those things showing up, you need to go back and make sure that they show up. Now, at this point, you could simplify, but don't. Just plug in. Plug in everything you know. So now we're going to plug in. So we have dy dt equal to negative 1 times 1 plus, if x is negative 3, then we have negative 3 squared, which is positive 9. The negative second times 2 times negative 3 is negative 6. And dx dt is 2. And if I didn't have time to do any more, I might just slap on an inches per second and leave it at that. Right? I don't really actually need to simplify that. I should, like, it's better to simplify it. But if I was pressed for time or felt like I was going to be pressed for time, leave it there and then come back to it later. But this is a perfectly good answer. If we simplify it a little bit, writing things with positive powers, the negative 1 times the negative 6 times the positive 2 is going to be 12 on top. On the bottom, I'm going to have a 10 to the positive second. Or if you prefer, 12 over 100 inches per second. Yeah, you could reduce that to 6 over 50 or 3 over 25, but why? It is good practice to simplify things as much as you can, but use your time efficiently. Don't, right? This step here, from here to there, is maybe worth a point. Or maybe, it depends. But like, it's not the bulk of the points on this question. All right, let's look at the next one, which is a little bit harder, I think. So the one I wrote for this, my problem 2B on my practice exam is definitely harder than this one because you have to use the product rule as well. So I would encourage you all to do that one. I think it's a good problem. Well, let's take a look here. So we've got x squared plus y squared equals z squared. Find dz dt when x equals 3, y equals 4, dx dt equals 2, dy dt equals 7. Okay, so let's just take this and differentiate both sides. All right, you all should do this. You have x squared plus y squared equal to z squared. Take the derivative of both sides. I will give you 30 seconds. All right, it's been 30 or 40 seconds. So the derivative of x squared is 2x times dx dt. The derivative of y squared is 2 times my stuff times the derivative of my stuff, or 2y times dy dt. And the derivative of z squared is 2 times z times dz dt. Cool. Plug in. So they told me x equals 3 and y equals 4. So I'm going to get 2 times 3 times dx dt is 2. Y was 4. 2 times 4 times dy dt was 7. 2 times, they didn't tell me what z is. No, it doesn't matter. Order of multiplication doesn't matter. I'm just always thinking of it as take like derivative of some stuff squared is 2 times my stuff, and then after that multiply by the derivative of the stuff. But it's totally fine to write dx dt in front. They didn't tell me what z is. But I have what x is, what y is, and an equation relating x, y, and z. So I can find out what z is. This is interesting. So this problem technically is not written as specifically as it needs to be. It's fine. But here's the mild issue that you shouldn't really worry about. If we say that 3 squared plus 4 squared equals z squared, 3 squared plus 4 squared is how much? Right, 25. And if z squared equals 25, what's z equal to? Or, right, so technically z could be positive 5 or negative 5. And he didn't specify that z had to be positive. So I imagine he meant for z to be positive, but if something like that comes up, you might ask. You might not. You might just be like, yeah, okay, z is positive 5. But you might right here z equals plus or minus 5. And you'd be like, okay, we're going to pick that one. You're like, you should have been more careful with your test writing. It happens, though. You don't always see the things until someone else points it out to you. So then we would add this together. 2 times 3 times 2 is 6 times 2, which is 12. 2 times 4 times 7 is 8 times 7 is 56. And then divided by 10. That's going to be dz dt. And yeah, we could simplify that. It's going to be 68 divided by 10. Or if you prefer, 6.8. I don't usually prefer decimals, but if it's division by 10, it's pretty easy to make it a decimal. Cool. How about some of the optimization stuff? Let's see here. I will say this practice exam feels a little bit longer than his other practice. Like, I don't think his actual exam is going to be this long. I just feel like he had, I mean, I hope it's not going to be this long because this feels too long to me. But I feel like he had a lot of things like he wanted to be like, oh, I feel like there was just a lot of things he wanted to make sure he presented in the practice exam. So I wouldn't imagine it's actually going to be that long, but it could be. Just don't think it will. Okay, let's look at, of course, I've written here. So let me give myself some more paper. I'm like, what was that? Pile my paper for myself. Okay. So let's look at problem 7A. A farmer has 100 feet of fence and wants to make 3 adjacent rectangular corrals. The corrals will use the best design of being side by side and sharing the middle fences. So it's not always easy to interpret what is being described here. This is what he means. He means your corrals look like this. 3 adjacent rectangular corrals, sharing middle fences, make a sketch and clearly indicate your variables on the sketch. There's 2 different ways of doing this. My preference is to call this side whatever. This is X. And we do have to write X's there because we do have to use fence to build those middle parts as well. And then some people like to call each of these parts Y. I like to say this whole side is Y. I feel like that is easier to me. And yeah, and we have a Y up there as well. Okay, almost always whenever you're doing optimization, there are 2 equations you have to write down. The thing you're trying to optimize, aka maximize or minimize, and the constraint, the limiting piece of information. So here, what are we trying to maximize or minimize? Right. These optimization questions are as much a reading question as they are a math question. you have to be able to read the question critically quickly. So we're going to maximize the area. Okay, based on my picture, what's my formula for area? Area of a rectangle is what times what? X times Y, base times height, length times width, whatever you want to call it. Here, that's also why I wrote Y here instead of Y plus Y plus Y, because then it would be X times 3Y, which is not terrible. It's just not as nice. How many variables I got there? How many variables? Two, too many. So we need, of course, a constraint. Remember, right? If you see two, it's too many. That means we need a constraint. And we are constrained by the fact that we have 100 feet of fence to use. Okay, so all of the places where we are building fence contribute to the fence we're going to build. That sounded like a dumb sentence, but yeah, I hope it's made sense, right? Our x plus x plus x plus x plus y is going to add up to 100 because that's how much fence we have to use, and we have to distribute it among those 6 sides of our pen. So I would say 4x plus 2y is equal to 100. You can solve or isolate either variable, but I'm going to tell you here it would be nicer if we isolated y. Because if we isolate x, we're going to have to divide everything by 4, and we're going to have a fraction if we do that. So it's fine to do that. It's just a little bit easier if we decide to say 2y equals 100 minus 4x, and then divide everything by 2 to get y equal to 50 minus 2x. That's going to work a little bit better. Plug that back in. So now we're trying to maximize area, and it's going to be a function of just one variable, x. You do not have to write a of x, but I like to. And it's going to be x times 50 minus 2x. And to make our lives easier, okay, so if we're trying to maximize this, what are we going to do? Instead is equal to? Right. But before doing that, I think it's going to be beneficial. I don't want to use the product rule if I don't have to. It's much easier just to multiply this out and say it's 50x minus 2x squared. Derivative is going to be 50 minus 4x. Set that equal to 0. Solve for x. You're going to get 50 equal to 4x, or 50 divided by 4 equal to x, or 25 divided by 2 equal to x. Almost always, at the moment I find my critical value, I go back and read the question. So once you find what x is, go read the question. Okay, farmer has 100 feet of fence, wants to make 3 corrals. Corrals use the best design, blah, blah, blah. Make a sketch, indicate your variables. What dimensions should be used so that the enclosed area will be a maximum? So I found one of the dimensions. X is going to be 25 over 2. Is it feet? Yeah, it's feet. How am I going to find y? The other dimension. The other dimension, the other dimension, the other dimension, the other dimension. Oh, sorry. Anyway, so you're going to find y by looking at where you have y equals, right? The other dimension you're trying to find, almost always you have exactly the equation you need when you isolated something to deal with the constraint. So y is going to equal 50 minus 2 times your x value, which is going to be 50 minus 25, which is equal to 25. So y is equal to 25 feet. Cool. And I am personally happy to see that on this exam, he is asking you to then verify or prove that the thing you have found actually is maximizing the area. And in my opinion, there's 2, maybe 3 good ways of doing this. Let's talk about that. So how do we prove that the critical value you found, x equal to 25 over 2, does in fact maximize the area? Okay. In this problem, the way I think the easiest way to do this is the second derivative test. In fact, I feel like that's kind of my go-to for these optimization problems. So take the second derivative, a double prime. If I look at my function here, a prime is 50 minus 4x. A double prime is -4. I can't even, well, I should say, it takes literally no effort to plug in my critical value. So if I plug in what my critical value is, a double prime of 25/2, what's that going to be? -4. All right, so if my second derivative, my critical point is negative, what does that mean I have? A maximum or a minimum? Right, the thing that we are asked to show that we have, right? He's not going to ask you to show that you have a maximum and then secretly make it a minimum. Or, I mean, if he does, that's a real not nice move. But the reason you're right is because at that point, it's concave down. If it's concave down, you have a maximum. So I would maybe write, I really do like to write concave down. Oh yeah, we have a max. You're very welcome, Nikki. Good luck on your exam. The other way you could do this would be to kind of do a first derivatives test sort of thing and say, okay, well, we know that now I should say for the first derivative test kind of thing, you also have to think about the domain of the function. If you look at this thing I've drawn here, what's the smallest reasonable value for x? Or maybe even a little unreasonable. Could x be negative? Of course not. You can't have a negative side length. Could x be 0? Sure, it'd be kind of weird, but people are okay with that usually. Okay, here's a more interesting question. What's the biggest x could be? It couldn't be 100, but you're on the right track because there isn't just one x, there are how many x's? So 4x could be as big as 100. So x could be as big as 100 divided by 4, which is 25. And then we could do like a first derivative test kind of thing and say, okay, well, if I look at my first derivative here, which is 50 minus 4x, if I plug in the number bigger than 25/2, like 24, or maybe even 20, 50 minus 4 times 20 is negative. I'm plugging something smaller than 25/2, like 1, 50 minus 4 times 1 is positive. Increasing, decreasing, yes, we have a max. The third option, which is not always an option, but it is an option here, is to use the extreme value theorem. And to say, oh, look, my function a of x equal to x times 50 minus 2x has a domain, a natural domain, or an implicit domain, sure, has a domain of 0 bracket to 25 bracket. It is a continuous function on a closed interval. By the way, for the extreme value theorem question he asks on at the end of the exam, the statement of the extreme value theorem, all you really have to say is that to use the extreme value theorem, you have to have a function that is continuous on a closed interval. I would say, back up. If you have a function that is continuous on a closed interval, then you have to have an absolute maximum and an absolute minimum somewhere in that interval. That's essentially the extreme value theorem. That's how I would write it down in words. So this is continuous everywhere. We have a closed interval, so you have to have an absolute max and an absolute min somewhere at either the critical point or one of the endpoints. Well, take a look at this. A of 0 is 0. A of 25 is 0 times, or sorry, 25 times 0. And A of my critical point is going to be not 0 and not negative. So it has to be the absolute maximum because you don't have any other choice. If I had to choose, I would choose the first way of doing it. To me, that seems the easiest. If it's easy to take the second derivative. Or sometimes taking the second derivative is not an easy thing to do, and so you shouldn't do it that way. Then maybe do one of these two things. But if you look at that first derivative where you found your critical values, you're like, oh yeah, taking the second derivative, this is really kind of a cakewalk. Do it that way. It is the easiest way to go, I think. Yeah. Well, because, I mean, because the question asks us to, right? If you look at, if you look at the practice exam, the second question literally is, use any method to prove the value you found in part A is a maximum. Not, well, so here, I would say no. So, I mean, yes, but the thing is, you're trying to prove that we maximized A of X. Now, I should point out, I feel like this is phrased a little bit poorly here, because we didn't actually find the maximum value of the function. We found the dimensions that maximize the value, the area. We didn't actually find the maximum area. That's okay. So, but when you're trying to show that the thing you found maximizes the thing, you only have to check. You only have to check the variable that you ended up writing your function as a variable. We only had to check X here because we wrote our area function as a function of just X. That's why. And that's typical. That makes sense? Okay. Now let's see here. What else? What time is it? 5 minutes. Anything specifically you'd like me to address in 5 minutes before I just pick something? All right, let's take a look real quick here. Sure. I will point out, at least as far as my reading goes, he didn't actually ask you to graph anything on this practice exam, right? No graphing? Okay. It's like all the stuff around graphing, but no actual graphing, which is nice for you. It's also nice for him as a grader, I think, because grading graphing is challenging, to be fair, because like not everyone's as good at drawing as everyone. So no graphing. I think there was something else I noticed that looked worthwhile here. Let me take a look here. So again, well, I'll remind you all, practice these. Make sure you can do each one of these in your sleep. You should dream about this tonight, because you know that's going to be probably the first question, but certainly a question on your exam. It's going to be there. You should skip to that one and do it first. Right? That is going to be yeah, I can do this, no problem. Got it down, done. Move on to the next one. We just did problem 2. Problem 3. Problem 3. Let's take a look here real quick. He's asking some definition questions. Now, that doesn't mean it's going to be on your test, but it's good to know. He definitely expects you to know this. So, what does it mean for x equals c to be a critical point of the function f of x? Well, 1, thank you. Excellent. F of c exists or is defined. And then 2, f prime of c is equal to, or, right, I would write f prime of c does not exist. I really, really would not write equals does not exist, because you don't like to say that. But if you wrote that, it wouldn't probably be a big deal. That's it. That's the whole thing. That's all I would write there. Cool. Let's see, problem 4. Let's see, we kind of did that one already. Yeah, let's look at this one for just a second. Yeah. Sure. How much time we got? Yeah, we got enough time. Okay. So looking at this, find f prime, simplify and write your answer without negative exponents. So f prime here is 6 times 2/3 times x to the negative 1/3 plus 4. We should definitely simplify that. 6 times 2/3 is 12/3, which is 4. So we got 4, and instead of times x to the negative 1/3, we should write it as 4 over x to the 1/3 plus 4. That's all I would do. I satisfied the requirement. I wrote the derivative without negative exponents. Awesome. Part 2, find the critical points. Okay, this is going to be a little more interesting. I'm going to take this. And before I even set it equal to 0, what value of x makes this undefined? 0. So x equals 0 is a critical value or critical point. Now let's set it equal to 0 and figure out what the other critical points might be. I don't love this, but yeah, sure, that's fine. So normally I might try and do some getting a common denominator or factoring here, but I think it's probably easier just to try and solve for x. So I would subtract 4 from both sides. Oh my gosh, okay, I can write. So 4 over x to the 1/3 equals -4. And I would probably multiply by both sides by x to the 1/3. So I'm going to get then 4 is equal to -4 times x to the 1/3. Divide both sides by -4. So 4 divided by -4 equals x to the 1/3. So that means that -1 equals the cube root of x. And if I cube both sides, you don't have to write the cube root of x. You can just write x to the 1/3. I just wanted to point out that they were the same. -1 cubed is still -1. And you're getting -1 equal to x. And you might, if you really like, if you weren't 100% sure, you might go back and plug it and be like, okay, -1, the cube root of -1 is still -1. 4 divided by -1 is -4, and -4 plus 4 is 0. So that checks out. Okay. Make a sign chart for the first derivative. Ooh, this one's going to be interesting. So I will point out that for our first derivative here, we didn't really factor it in any way, shape, or form. So it's going to be kind of hard to do the thing that I like to do, which is look at the factor a 0 came from, and then see if it's an odd or an even power to determine if we're changing or staying the same. Here, it's probably just going to be easier to plug in points to see what happens. So let's pick a point larger than 0. I might pick 1. What's 4 over 1 to the 1/3 plus 4? Is it positive or negative? Positive. 4 over a positive number plus plus 4 is definitely positive. Okay, between 0 and -1, I think things going to be a little bit dicey here. Very dicey, actually. Okay, if I pick a negative number, like -1/2, yeah, I don't like it, but it's what we've got. You might pick -1/8, because the cube root of -1/8 is -1/2, but I feel like that's not something everyone's gonna be like, oh yeah, pick -1/8. So -1/2, the cube root of -1/2 is negative. And it's also small. It's definitely less than 1. So if you have 4 divided by a number that's less than 1, is it getting bigger or smaller? Yeah. What's 4 divided by 1/3? 12. What's 4 divided by -1/3? -12. So when we divide by a small negative number, we get a large negative number, and a large negative number plus 4 is still negative. And then if we pick a larger negative number, now I would pick -8, because the cube root of -8 is what? -2. So -2, 4 divided by -2 is -2, -2 plus 4 is +2. So it's positive, so we're increasing, decreasing, increasing. So we have a relative maximum at -1, we have a relative minimum at 0. And I should stop talking because it is 10:22.